In this lecture, we're going to study dynamics. And dynamics is really the study of Newton's three laws of motion. I'm sure you've heard of these. First law is inertia. Second law is all about acceleration and forces. And the third law is about action and reaction pairs. So the do now, just pause the video and think of what you would say as the answers to the questions. And also take a look at the homework. You can write that down under classwork. So it's a separate piece of paper. Under classwork, you can write down this homework assignment that we'll do in class. So yeah, for now, just read the do now questions and think about answers to them. So if you saw a boulder in the middle of a flat field and it began to move, all of a sudden, you probably would look to see if somebody was pulling the boulder with a rope or pushing it with a stick, because you know that objects don't move unless a force is acting on it. And there is another option. This is going to come up a lot during this unit, is that when all the forces are on an object are balanced, so if like all the forces on this rock are balanced, we say that it's in equilibrium. And there's really two kinds of equilibrium. The first kind is called static equilibrium, and the second one is called dynamic equilibrium. But let's say that the object is in static equilibrium. If so, then we are also saying that that object is at rest. So objects that are in static equilibrium are at rest. And then the other kind of equilibrium is dynamic equilibrium, and it is still equilibrium because the forces are balanced, but it's dynamic equilibrium because the object is going to still be moving in dynamic equilibrium. And so that's the major difference. Is in static equilibrium, the object's not moving. In a dynamic equilibrium, the object will be moving. And both of them are okay as long as the object is not accelerating. So if the object isn't accelerating, it's in equilibrium. And if it's sitting still, it's static equilibrium, and if it's moving, it's dynamic equilibrium. All right, Newton's first law. You are supposed to have this memorized, so pay attention on this slide. According to Newton's first law, an object maintains a state of equilibrium, remaining at rest or moving with constant velocity unless acted upon by an unbalanced force. So one way that I've heard this stated before is I'll hear somebody say objects at rest stay at rest and objects in motion stay in motion. So that's another way of stating it. But basically it's like you have to just say that there's an unbalanced force, which is the opposite of what we were just talking about on the previous slide. And when you have this unbalanced force, it's going to cause an acceleration, and it's going to make the object either change from rest to being in motion or the opposite. So according to the first law, an unbalanced force always produces a change in velocity, so some kind of an acceleration. All right, good. So is an object accelerating if it changes its speed? Think about it, and then I'll have the answer when you come back. So the answer is yes. I didn't provide an explanation in writing, but if it changes its speed, you're meeting, let's see, this requirement, that unbalanced forces produce a change in an object's velocity. Second question, is an object accelerating if it changes its direction? I'll have the answer when you come back. So the answer is yes, and I actually have some of the same reasoning here, because it says, according to the first law, an unbalanced force always produces a change in the object's velocity. So one of the things that you're supposed to remember about velocity is that it's a vector quantity and includes direction. So that means if you're changing your direction, you are in fact changing your velocity. Even if the speed stays the same, a change in direction is a change in velocity. Thirdly, is an object accelerating if it changes its speed and direction? So the answer to that would be yes. Both changing your speed and direction are both ways of changing velocity. All right, so explain in terms of Newton's first law how this parlor trick is accomplished. Um, think about it, pause the video, and I'll explain when you come back. So Newton's first law says that objects at rest will tend to stay at rest. So this plate, this goblet, this candlestick, the reason why they're staying at rest, even when the tablecloth is pulled out from under them, is because they were at rest before the tablecloth was pulled. So objects at rest, stay at rest, should be taken quite literally in that way. But there is a second part of Newton's first law, which says that objects at rest stay at rest unless acted on by an outside force. And some people think about this tablecloth as, well, was this an outside force, though? Because I was able to grab the tablecloth and pull it, yet the other things that were on it stayed still. So that's why we would actually not consider this tablecloth a good source of outside force, because it was pulled very quickly, and it didn't have enough time really to grab on to these other objects on the table using friction. Then the outside force was really only on the cloth and not on these guys. And that's why they stayed still and the cloth moved. So for this slide, it's pretty simple. I just want you to pause the video and think about ways that each of these cartoons demonstrates Newton's first law. Both cartoons could be the same reason, different reasons, but it is two cartoons, top and a bottom. So here's my explanation for this one. There was definitely a force which was applied to the wagon, and that force would cause an acceleration. So the wagon accelerated. But since there was no force directly applied to the boy, then there was also no acceleration that the boy would experience. Therefore, when the wagon is pulled out from under him, he remains at rest. That's what I mean by no acceleration. And my explanation for the second one is that the strong man couldn't decelerate the truck to zero, given that he wasn't able to apply enough force to the truck to accelerate it all the way to zero. All right. You could also think about Newton's first law as the law of inertia. And inertia is a very important vocabulary word for you guys. I will circle it. It is basically an unwillingness that an object may have to change its motion. So that might mean that an object that's sitting still would resist being set into motion. Or it could mean that an object that is moving would resist stopping. And those are really two sides of the same coin. And the more mass you have, the more inertia you have. So it's the heaviest objects, the objects with the most mass, that would resist moving if they were at rest, and B, they would also resist stopping if they're already in motion. What you should know is that it is directly proportional to mass. And inertia actually has no relationship with really anything else but mass. So you'll see lots and lots of questions about inertia. And the thing that you should write down in your notes and that you should try to remember is that whichever object has the most mass, regardless of any other circumstance, it also has the most inertia. Inertia is the reason why it's really difficult for a little tugboat to push a large ship around. When these things are floating in water, their friction is very, very close to zero. So it's not friction that keeps the tugboat from doing a good job with the big boat. It's mostly just because the tugboat has a little mass and the big boat has a huge mass. So the larger the mass, the more resistant it is going to be to change its motion. And my last example for inertia on this slide has to do with seat belts. You guys know that if you're not wearing a seat belt and you're in a car, and that car hits an obstacle like a tree, the force of the collision would cause the car to slow down very rapidly. So it would cause a really negative acceleration for the car. But if the passengers aren't wearing seat belts, then one of the things that can happen is that they will not decelerate and they'll continue moving forward at the speed that the car was moving. And if that's the case, then they'll fly out of the car. It's extremely dangerous at that point. Anything can happen. So here's a little drawing that I would put in that would help you a little bit. So I just said that there's a person in the car who's moving forward with speed positive v, and then when the car hits the tree will produce a force that's in the opposite direction of v. So I said negative f, and that force will also cause an acceleration in the same direction as the force. So I said negative a. And that's going to cause the car to rapidly decelerate. But since there was technically no force applied to the person, because that person wasn't wearing a seatbelt, then the person would continue moving forward. So this is my summary of the argument. If you're not wearing a seatbelt, there will be no force put on you, there will be no acceleration put on you, and you will stay in motion. And this is just a restatement of my argument about the dog and the boy in the wagon. Since the dog put the force on the wagon, there was no force on the boy, and there was no acceleration for the boy, and so he stayed at rest. In this case, the person is staying in motion, but that's because Newton's first law actually goes for both of those directions. It says that objects at rest stay at rest unless acted upon by an outside force, and objects in motion stay in motion unless acted upon by an outside force. At this point, you've taken plenty of notes on Newton's first law. I will try to have this slide photocopied for you so that we can work on it together in class. And this slide contains the summary questions for Newton's first law. I will also try to have this photocopied for you in class so you don't have to copy it down. All right, Newton's second law is basically just this equation right here, which says that acceleration is F net over m. So this equation, it actually says a lot in a small space. It says that if you have an unbalanced force, which we just call a net force, if you have an unbalanced force in any direction, the acceleration will be in that same direction, and that the force and the acceleration are directly proportional to each other. That's why they're both in the numerators of this proportion. So they're directly proportional. And then the acceleration and the mass are, well, one's in the numerator and the other's in the denominator of the proportion. So that means they're inversely proportional. In short, if F goes up, A will go up. And in short, if M goes up, A will go down. And if M goes down, A will go up. So A and M opposites, but A and F are going to be the same. It's just a discussion about units, but just know that this is in newtons, that's kilograms, that's meters per second squared. And imagine that you were a guy who was putting a golf ball, and how that force that you would apply would cause an acceleration for the ball. But also, if you were trying to use the exact same force and putt a truck, how the outcome would be different. So it's just keep in mind that the forces are the same, but think about what's the major difference between the two, and pause the video, and then I'll have my explanation when you come back. So my very fast explanation is that acceleration and mass are actually inversely proportional, just like in this version of the equation. So if m goes up, then a goes down. So since the truck has a huge mass, this very large mass is going to lead to a very small, very tiny acceleration. On the other hand, an equal force to the one between the truck and the golf ball, an equal force on a small mass would give a larger acceleration. So in short, acceleration and mass are inversely proportional. So these three cartoons have three different scenarios. The first one, the dogs are pulling with a force of 100 newtons, and the mass is 50. And over in the second one, the dogs are pulling with 200 newtons of force, and the mass is still 50. And in the third one, it's 200 newtons in two different directions, and the mass would still be 50. Just putting in some units here. I just want you to think about what would happen in each of the scenarios. If you want to give a mathematical answer, go ahead and do it. I think you could probably do it in your head. But you should expect three different accelerations on the three different cartoons. All right, so first one, I would just say that the acceleration is 2 meters per second squared. I figured that out because I was just thinking that A is going to be F net over M. So if F is 100 and M is 50, then A would have to be 2. And I did say it would be to the left because it's going to be in the same direction as the force. I used that very same logic over in the second one, A equals F naught over M, but I got an acceleration of 4. And in the third one, I used the same logic actually. The difference is that F net in this case was 0 because we have equal forces pulling on the left and on the right. So it's going to produce an acceleration of 0. Newton's second law also has a connection to graphing, which I think you can appreciate. I would start by just thinking that A equals F over M, and then we'll rearrange so that it says F equals MA. And then lastly, I want to solve for M, so I'm going to say that mass is F over A. Essentially, I just used order of operations and isolation techniques there. So if I want to calculate the mass of an object, and I have information about its acceleration and its force, then the way that you could calculate the mass is actually by doing something like a slope. It's not exactly a slope, because I do know that slope is, to be sure, slope is rise over run. So that means that in this case, the slope technically would be A over F, which of course is not the same thing that I just solved for. So what you can do is you can think of like an inverse slope, or a slope to the -1. And that would be, in this case, F over A. So instead of getting fancy, what I actually suggest, if you're able to recognize that you need to do F over A to get the slope, then instead of doing rise over run, why not just do run over rise, or the change in x over the change in y? In the explanation right here in the text, it's doing a normal slope, normal slope, normal slope, but then it's suggesting doing 1 over your answer. So I would just say do run over rise. You'll still get 2.5, by the way. So take a moment for yourself and pause this video and read through the cartoon. When you have had a chance to read it, come back and I'll have an explanation. So in summary, there are two arguments. One argument says that this bag of clothespins, because it has a large force pulling on it, meaning that it has a lot of weight, that it'll accelerate faster. Basically, we know that A equals F over M, and the relationship between F, or the weight of the bag, and acceleration is a direct relationship. So the larger the F, the larger the acceleration. So one person claims that this bag of clothespins will accelerate much faster because it has a lot more force. On the other hand, there's another argument, which is that the smaller one, the clothespin itself, has less mass, and therefore it has less inertia. So you might remember that there's a direct proportionality between mass and inertia. So since the smaller one has less mass and less inertia, then you would expect it to resist a change in its motion less, and therefore it would get going faster, I guess you could say. And therefore it would accelerate faster. So which one is correct? As it turns out, both of these interests are competing. More force would give more acceleration, but less mass is also less inertia. So it'll have an easier time getting started. So in the end, the both effects cancel each other out, and what you'll expect is that the acceleration of both is the same. It's a little anticlimactic, but it's true. All right, let's work on these practice questions for Newton's second law. The first question says that a 10 Newton force gives a mass, m1, an acceleration, a, and a 20 Newton force gives another mass, m2, the same acceleration, a. What's the ratio of m1 to m2? One of the things that I think could be helpful here is a little bit of algebraic manipulation. I can see that both of these masses are going to have the same acceleration, a. So what I'm going to do is I'm going to write the equation a equals f net over m for both of them, but I'm going to set them equal to each other at a. I'll show you what I mean. So I've written a equals f over m in red and in blue. Red is representing, I guess, mass 1, and blue represents mass 2. And they both have the same value for a, so I'm going to set them equal to each other at a. So going from here, they just want to know the ratio of m1 to m2, or they want to know the ratio of this guy to this guy. Since they did go ahead and tell me that the force that's on mass 1 is a 10 Newton force, and that the force on mass 2 is a 20 Newton force, then I can assume that since these two proportions have to be equal to one another, that the proportion of m1 to m2 has to be the same as the proportion of f1 to f2. So you could say 10 to 20, or you could say 1 to 2. Okay, so my second question. It says the diagram at the right shows two forces, F1 and F2, that are both applied to a 2 kilogram box that's originally at rest on a horizontal frictionless surface. Calculate the magnitude and direction of the acceleration of the box. So in order to know the magnitude and direction of the acceleration of the box, I need to know F net, which is the overall set of forces that's acting on the box. But this is complicated because I have more than one force acting on this box, and unfortunately, one of them is sort of up in the air, meaning that I can't simply subtract it from the three. Instead, I'm going to have to do a bit of trigonometry, and to draw, I can draw a triangle here that'll help you understand what I'm about to do. A lot of this 10 Newton force is going up in the air, up and to the right, at an angle of 30 degrees above the horizontal. And that means that a portion of that 10 Newton force is going to give us a component force, which is called AY. And another portion of that force will give us a horizontal component force, which is called AX. One thing I'm asking you to consider right now is that since F1 is horizontal, and AX is horizontal, that those are the two forces that are going to combine to give you F net. And actually, AY, it doesn't give us anything that we need at all. So I'm just going to put a big question mark over AY. We don't need it for this question. All right, so let's solve for AX. The easiest way to do that is to say that AX is A cosine theta. I'll give you a second now to calculate that, but it's going to be the hypotenuse, which is 10 newtons, multiplied by the cosine of 30. So I just solved it, and I was able to find that AX is going to give you a value of 8.66 newtons, and that is to the right. But keep in mind there is another force, and I'll do that one in blue, of F1, which is negative 3.0 newtons. I am using negative, by the way, because it's to the left, whereas this force is to the right. So one's to the right, one's to the left. I just have to make one of them negative. When I combine these two forces together, it's going to give me an F net. And the F net is going to be 8.66 minus 3. So I'm going to get 5.66 newtons. The direction on that is going to be the same direction as whichever one was larger. So that's going to be the direction of AX. So that's to the right, by the way. So I'm getting 5.66 newtons to the right. Now the thing is, I don't think I've answered the question yet because they want to know the magnitude and direction of the acceleration of the box. And all I've done so far is to find the magnitude and direction of the force of the box. So in order to find an acceleration, I have one more step. And that is that A equals F net over M. The F net is 5.66 newtons, and the mass is 2. So that means that my overall acceleration is going to be, excuse the pause in the video there, I had to calculate it. It is 2.83 meters per second squared. And that is also to the right. So 2.83 meters per second squared to the right. All right, so we are at the pair up for Newton's second law. I will try to get these copied onto photocopy paper for you guys, so that you can work on them in class. And this summary I'll also try to get it copied onto photocopy paper so that we can work on it in class together. So Newton's third law is, oh gosh, it's the best and the worst of Newton's laws. The best thing about it is that there really isn't any math that could even possibly go with this question. And another thing that's really good about it is that if you follow its very simple rule to the T, you will never miss any question about Newton's third law. I think the thing that makes it also the worst is that it is really hard for you to overcome your internal misconceptions about how this law works. And you will probably, even though you know perfectly well what this law says, you'll probably break it from time to time. So without further ado, Newton's third law. It basically says that whatever force is put on one object, that object will put the exact same force onto the other object. It'll just be in the opposite direction. So in the case of a hammer and a nail, if the hammer is swinging down with a force of 50 newtons, then the nail is going to push up with a force of 50 newtons. And, you know, this is kind of weird, right? Because it's almost like a lot of people understand this a little bit mistakenly, but a lot of people understand it to think that if the hammer swings down with a force of 50 newtons and the nail pushes up with a force of 50 newtons, then a lot of people are thinking, oh, well then isn't the net force 0 and wouldn't the nail stay in place? And this is where it gets it gets complicated, which is that no, a force from the hammer going down to the nail does not cancel a force from the nail going up to the hammer. So you have to think of those as two separate forces. One on a nail and the other force is on the hammer. So a force on a hammer could never cancel the force on the nail. So I think that's where it gets tricky. We can go through a couple of examples here. I'll give you my explanations, and you'll have probably questions in class. And I have some pair-ups after this. So here's an example. A baseball bat striking a ball is an example of an action-reaction pair. If the bat exerts a 50 Newton force on the baseball, then the ball exerts a 50 Newton force on the bat in the opposite direction. Or in other words, both members, the bat and the ball, were members of an action-reaction pair, and they produced equal and opposite forces. So here's a question. It says, for the hammer nail example, identify the action-reaction pair and cite the evidence that the nail exerts an equal and opposite force on the hammer. So think of this as an action-reaction pair, and then just describe it. So it's pretty easy to describe an action-reaction pair. This is what I would say. Hammer exerts force on nail, and nail exerts force on hammer. That's a description of the action-reaction pair. Now, evidence that the nail is definitely exerting a force on the hammer, you probably would have had to have hammered a nail at some point to get this one, but the evidence is that when the hammer hits the nail, the hammer slows down, meaning it's received a negative acceleration. And the only way that can happen is if there is a force pressing up from the nail to the hammer. That's the only way it can get a negative acceleration. Here are 3 examples of action-reaction pairs. The first one is responsible for why a car moves forward when the tires move forward. So the action is that the tire pushes on the road, and the reaction is that the road pushes backward on the tire. So as the tire spins like this and pushes backward on the road, the car wouldn't move forward unless the road was able to push forward on the tire. So tire pushes backward on the road pushes forward on the tire. Second example, if you're in a rocket, you are basically accelerating because you're expelling gas. So basically, as the gas is pushed backward by the rocket, the gas pushes the rocket forward. So rocket pushes backward on the gas pushes forward on the rocket. Last example. This one may be a bit hard for some of you to accept, but if you drop an object from a height, it is pulled downward by the force of gravity. But an equal and opposite force that you maybe haven't thought about before is that the gravity that the ball has actually pulls upward on the Earth, and they're pulling on each other with equal forces, which means that if the Earth pulls down on the ball with a force of 50 newtons, the ball pulls up on the Earth with a force of 50 newtons. All right, so in terms of Newton's third law, let's say you're walking across the floor. The way that this actually occurs is that you push backward on the floor pushes forward on you. Let's say that you're swimming through water. In terms of Newton's third law, the way that works is that you push backward on the water pushes forward on you. Thirdly, let's say that you blow up a balloon and then release it and it flies across the room. That's because the balloon pushes backward on the gas and gas pushes forward on the balloon. So as for these demonstrations, if you guys remind me, I will get some materials together and I'll do them for you. Otherwise, I can't do them over this video. So I think this cartoon it's basically everything when it comes to Newton's third law. I'll walk you guys through it. So basically there's a horse, and he's thinking about Newton's third law and how there are equal and opposite forces. And he's thinking that if he pulls on the cart, that the cart will pull back on him with an equal force, and that means he'll have a zero net force, and that he won't be able to accelerate. And the dude that's in the wagon in the back thinks about physics a little bit, and he basically says that, listen, there are 2 separate forces here. One of them is a force that you're exerting on the cart, and the other one is a force that the cart exerts on you. And he's saying he doesn't care about the force that is exerted on the horse. He's only caring about the force that's exerted on the cart. And if he exerts a force on the cart, then it'll produce an acceleration. And the horse wonders a little bit further, how could he move forward if the cart is pulling back on him? And all the guy is saying is all you have to do is push on the ground. And if you push on the ground will push you forward. And therefore, you'll be able to pull the cart. So the takeaway here is that a force on one object cannot cancel a force on a different object. So it is true, Newton's third law says that there are equal and opposite forces in an action-reaction pair, but just know that that doesn't mean that there cannot be acceleration. So we've reached the pair up for Newton's third law. I'll try to have this photocopied for you so that we can work on it in class. And then there's the summary as well, which I'll also try to photocopy for you to work on in class.